Not every machine was banned because it failed. Some were outlawed because they worked too well, causing damage so widespread that governments could no longer justify their continued use. These heavy machines delivered power, efficiency, and profit by exposing workers, communities, and environments to risks that proved impossible to contain. Poison spread through air and water. Infrastructure collapsed under mechanical force, and invisible hazards accumulated long after operations ended. In each case, regulation came only after the consequences crossed national boundaries and public tolerance collapsed. What unites these machines is not poor engineering, but a design philosophy that placed output above survivability. When their harm became undeniable and irreversible, entire countries stepped in to ban, restrict, or erase them, leaving behind lessons written in law, contaminated landscapes, and lives permanently altered. Asbestos spraying machine, industrial insulation that poisoned entire generations. The asbestos spraying machine was once considered a miracle of modern construction, capable of coating steel, concrete, and ship hulls with fireproof insulation in a matter of minutes. In reality, it became one of the most devastating industrial machines ever deployed, spreading lethal fibers into workplaces, cities, and human lungs on a scale that few other technologies have matched. Asbestos spraying machines emerged in the early to mid-20th century, particularly during periods of rapid industrialization and wartime construction. They were widely used in shipyards, factories, power plants, schools, and high-rise buildings. The machines mixed loose asbestos fibers with binders and water, then projected the slurry under pressure through hoses and nozzles, coating surfaces with thick insulating layers. The process was fast, cheap, and extremely effective at resisting fire and heat. The danger lay in how the machines worked, spraying atomized asbestos into microscopic airborne fibers that remained suspended for hours. These fibers were invisible, odorless, and easily inhaled. Operators stood directly in dense clouds of asbestos dust, often without masks or ventilation. Nearby workers and even people outside the building were exposed as fibers drifted through open doors, windows, and ventilation systems. At the time, asbestos was marketed as safe. Manufacturers downplayed or concealed evidence of harm, even as medical studies began linking asbestos exposure to lung scarring and fatal cancers. The spraying process dramatically increased risk because it produced loose, friable asbestos, the most dangerous form. Once inhaled, fibers lodged permanently in lung tissue, triggering diseases decades later. The human toll was immense. Workers who operated spraying machines developed asbestosis, lung cancer, and mesothelioma at staggering rates. Entire shipyard and construction workforces were affected, followed years later by teachers, students, and office workers who occupied contaminated buildings. Families were exposed secondhand as fibers clung to clothing and hair, poisoning spouses and children. Environmental contamination made the problem national in scale. Sprayed asbestos deteriorated over time, shedding fibers into indoor air long after installation. Renovation or demolition released massive quantities again, turning buildings into toxic hazards. Cleanup costs reached billions, and some structures were abandoned entirely. By the late 20th century, evidence was undeniable. Countries across Europe, Asia, and the Americas banned asbestos spraying outright, followed by broader bans on asbestos use. Courts ruled that manufacturers had knowingly endangered lives, leading to historic lawsuits and compensation claims. The asbestos spraying machine stands as a warning of how industrial efficiency can eclipse human safety. It did not explode or crush, but quietly contaminated generations. By transforming a toxic mineral into airborne dust at industrial scale, it became a machine whose legacy is measured not in output, but in lives irreversibly damaged long after the machines were switched off. Mercury gold dredge, river mining that contaminates nations. The Mercury gold dredge was once hailed as a breakthrough in mineral extraction, capable of stripping gold from riverbeds with unprecedented efficiency. In reality, it became one of the most environmentally destructive heavy machines ever deployed, contaminating entire river systems and poisoning human populations on a national scale. Its damage was not confined to a work site. It spread downstream, across borders, and through generations. Mercury gold dredges emerged in the late 19th and early 20th centuries, particularly during gold rushes in North and South America, Africa, and parts of Asia. These floating industrial platforms used mechanical buckets or suction systems to excavate sediment from riverbeds. The dredged material was processed on board, where mercury was introduced to bind with fine gold particles, forming an amalgam that could be separated and later heated to recover the metal. The danger lay in mercury's behavior during dredging. Large quantities of liquid mercury were poured directly into open sluices and processing trays. Inevitably, significant amounts escaped into the river with tailings. Unlike solid waste, mercury did not settle harmlessly. It dispersed through water, bound to sediments, and was converted by microorganisms into methylmercury, a highly toxic compound that bioaccumulates in fish and wildlife. Rivers subjected to dredging became long-term contamination sources. Fish absorbed mercury into their tissues, which then passed into birds, mammals, and human populations that relied on river ecosystems for food. Communities far downstream, with no involvement in mining, experienced elevated rates of neurological damage, birth defects, and developmental disorders. Symptoms included tremors, memory loss, impaired motor function, and cognitive decline. The scale of damage was amplified by the dredges themselves. Unlike small-scale mining, dredges operated continuously and processed vast volumes of sediment. Riverbanks were destabilized, habitats destroyed, and natural sediment flow permanently altered. Combined with mercury pollution, entire river systems were rendered ecologically and economically unviable. For decades, the danger was ignored or minimized. Mercury losses were considered an acceptable cost of extraction, and responsibility for downstream effects was rarely acknowledged. By the mid-20th century, scientific evidence became impossible to dismiss. Studies linked dredging operations directly to widespread mercury contamination, prompting public outcry and regulatory action. Many countries responded by banning mercury-based dredging outright. In the United States, Canada, and much of Europe, such operations were prohibited or tightly restricted. Similar bans followed in parts of South America and Asia as the long-term health consequences became clear. Cleanup efforts proved extraordinarily difficult, as mercury embedded in sediments can remain toxic for centuries. The mercury gold dredge represents industrial harm at its most expansive. It transformed rivers into extraction machines while turning entire watersheds into toxic legacies. Unlike accidents that kill immediately, this machine poisoned slowly and invisibly, earning its place among heavy machines so destructive that nations were forced to ban them entirely. Steam traction engine, road locomotive, public infrastructure destroyer. The steam traction engine, often called the road locomotive, was one of the earliest attempts to bring heavy mechanical power onto public roads. While it promised to revolutionize transport and haulage, it quickly earned a reputation as a machine so destructive and dangerous that entire countries were forced to restrict or ban its use. Its failure was not technical alone, but social, economic, and infrastructural. Steam traction engines appeared in the mid-19th century, designed to haul loads far heavier than horse-drawn wagons. Weighing anywhere from 10 to over 30 tons, these machines rolled on rigid iron wheels and were powered by large steam boilers operating under high pressure. On private land or prepared surfaces, they could perform impressively. On public roads, they became disasters on wheels. The primary problem was weight. Most roads of the era were never designed to support concentrated loads of that magnitude. As traction engines moved through towns and countryside, they crushed stone road surfaces, shattered paving blocks, and collapsed poorly reinforced bridges. Roadbeds rutted deeply under their wheels, turning streets into mud traps that became unusable for weeks. Local governments faced constant repair costs that far exceeded any economic benefit the machines provided. Vibration added further destruction. The engine's pistons, gears, and steel wheels transmitted intense shock into the ground. Buildings near roads cracked, walls fractured, and underground utilities were damaged. In some areas, residents reported structural damage to homes simply from repeated engine traffic passing nearby. Safety risks were equally severe. Steam traction engines moved slowly but had enormous momentum. Braking systems were crude, and stopping distances were long. On narrow roads, collisions with pedestrians, carts, and livestock were common and often fatal. Boiler explosions, though rare, occurred in public spaces when they did, killing bystanders who had no connection to the machine's operation. The machines also terrified animals. Horses panicked at the noise, steam, and smoke, leading to runaway accidents that injured riders and damaged property. Farmers and transport operators protested, arguing that traction engines made roads unsafe for traditional traffic. Governments responded with legislation. In Britain, the infamous Red Flag Acts required a person to walk ahead of road locomotives waving a red flag and limited speeds to a crawl. Similar restrictions appeared across Europe. In many regions, these laws effectively banned steam traction engines from public roads altogether, confining them to farms, quarries, and private haulage routes. By the early 20th century, lighter internal combustion vehicles replaced steam road locomotives, rendering them obsolete. Their decline was not due to lack of power, but because their power was incompatible with public infrastructure. The steam traction engine stands as an early lesson in unintended industrial consequences. It proved that introducing heavy machinery into shared public spaces without structural adaptation can cause more harm than progress. Powerful though it was, the road locomotive destroyed the very networks it depended on, earning its place among machines banned not for inefficiency, but for sheer incompatibility with society itself. Lead paint grinding machine, mass production of a neurotoxin. The lead paint grinding machine was a cornerstone of early industrial coatings manufacturing, and, in hindsight, one of the most quietly devastating machines ever put into widespread use. Designed to pulverize lead compounds into fine pigments for paint, it enabled mass production of durable, colorful coatings while simultaneously dispersing a potent neurotoxin into factories, cities, and homes on a national scale. Lead-based pigments had been used for centuries, but industrial grinding machines introduced in the 19th and early 20th centuries transformed production volume. These machines used heavy stone rollers, steel mills, or rotating grinders to crush lead carbonate, lead oxide, and other compounds into ultra-fine powders. The finer the grind, the better the paint's coverage and durability. Unfortunately, the finer the powder, the more dangerous it became. The primary hazard was airborne exposure. Grinding machines generated dense clouds of lead dust that filled production rooms continuously. Ventilation was minimal, and workers often labored in enclosed spaces where dust settled on skin, clothing, food, and lungs. Protective equipment was rare or non-existent, as lead toxicity was poorly understood or deliberately ignored by manufacturers prioritizing output. Inhalation and ingestion caused cumulative poisoning. Unlike acute industrial accidents, lead exposure built slowly over time. Workers developed chronic headaches, abdominal pain, tremors, anemia, and progressive neurological damage. Many suffered permanent cognitive impairment, paralysis, or organ failure. Symptoms were frequently misdiagnosed, allowing exposure to continue unchecked. The danger extended beyond factory walls. Lead paint produced by these machines was applied extensively in homes, schools, hospitals, and public buildings. As paint aged, flaked, or was sanded during maintenance, lead dust entered living spaces. Children were especially vulnerable, absorbing lead more readily and suffering irreversible brain damage, learning disabilities, and behavioral disorders. Grinding machines amplified the threat by standardizing and scaling production. What had once been localized artisanal exposure became national contamination. Entire urban populations were affected, particularly in low-income housing where lead paint persisted longest. The machine's efficiency ensured that lead exposure was not an accident, but a systemic outcome of industrial design. Medical evidence mounted throughout the early and mid-20th century, linking lead paint directly to widespread poisoning. Public health studies revealed alarming rates of childhood lead exposure, forcing governments to confront the scale of harm. By the late 20th century, many countries banned lead-based paints entirely, effectively rendering lead paint grinding machines obsolete. Cleanup proved far more difficult than production. Lead does not degrade and remains embedded in walls, soil, and infrastructure decades later. Billions have been spent on remediation, yet exposure risks persist in older buildings. The lead paint grinding machine stands as a grim example of industrial success masking long-term catastrophe. It did not explode or collapse, but steadily manufactured harm at scale. By turning a toxic metal into a ubiquitous household product, it became a machine whose legacy is measured not in profit or productivity, but in generations of neurological damage that could never be undone. Early nuclear reactor. Graphite moderated, no containment, power without a safety margin. Early graphite-moderated nuclear reactors without full containment structures represented one of the most dangerous technological gambles of the 20th century. Built during the formative years of nuclear power and weapons production, these reactors generated enormous energy, while operating with virtually no margin for error. When they failed, the consequences extended far beyond industrial accidents, contaminating entire regions and forcing nations to reconsider the limits of acceptable risk. Graphite-moderated reactors were developed in the 1940s and 1950s, primarily for plutonium production and early power generation. They used graphite blocks to slow neutrons and maintain a nuclear chain reaction, while water or gas removed heat from the core. The design allowed reactors to operate using natural uranium, a strategic advantage at a time when enriched fuel was scarce. However, this benefit came with profound safety compromises. The most critical flaw was the absence of robust containment. Many early reactors were housed in simple industrial buildings rather than reinforced concrete domes. They were never designed to withstand core damage, explosions, or large-scale radioactive release. If the reactor became unstable, there was nothing to prevent radiation from escaping directly into the environment. Control systems were crude by modern standards. Reactor behavior was poorly understood, and some designs exhibited dangerous positive feedback characteristics, meaning power output increased as conditions worsened. Operators relied heavily on manual controls and limited instrumentation. A misjudged adjustment or mechanical fault could cause rapid power excursions that overwhelmed cooling systems in seconds. Graphite itself introduced additional hazards. Under extreme heat, graphite can ignite, producing fires that are difficult to extinguish and capable of lofting radioactive material high into the atmosphere. Once burning, graphite acts as a powerful dispersal mechanism, spreading contamination far beyond the reactor site. Worker exposure was severe, even during routine operation. Maintenance crews operated close to reactor cores with minimal shielding, often receiving radiation doses that would be considered unacceptable today. Accidents during refueling or component replacement exposed personnel to lethal radiation, sometimes with fatal effects days or weeks later. When failures occurred, consequences were national or international in scale. Radioactive fallout contaminated land, water, and air, forcing evacuations and long-term exclusion zones. Agricultural regions were rendered unusable, and public trust in nuclear technology collapsed almost overnight. As evidence of these dangers accumulated, countries began shutting down or radically redesigning graphite-moderated reactors. Modern nuclear plants incorporated negative feedback systems, multiple layers of containment, automated shutdown mechanisms, and comprehensive safety analysis. Reactors lacking these features were deemed too dangerous to continue operating. Early graphite-moderated reactors without containment demonstrated the peril of deploying powerful technology before understanding its behavior. They produced energy and strategic material, but at the cost of safety principles still being written. By operating without a true safety margin, they forced entire nations to confront the reality that some machines are too dangerous to trust, regardless of their potential. Chlorine gas compression plant. Industrial-scale chemical weaponization. The chlorine gas compression plant was one of the most dangerous industrial installations ever built, operating at the boundary between civilian manufacturing and chemical warfare. Designed to compress, store, and distribute chlorine at industrial scale, these plants turned a highly toxic substance into a routine commodity, while creating conditions where a single failure could kill thousands within minutes. Chlorine compression plants expanded rapidly in the late 19th and early 20th centuries as chlorine became essential for water treatment, paper bleaching, chemical synthesis, and sanitation. To transport and store chlorine efficiently, plants compress the gas into liquid form using powerful compressors, thick-walled pipes, and high-pressure storage tanks. In theory, this made chlorine manageable. In reality, it concentrated extreme lethality into dense, confined systems. Chlorine is a choking agent that damages lungs, eyes, and skin upon exposure. At high concentrations, it causes rapid respiratory failure. Compression plants handled vast quantities under pressure, meaning leaks were not slow or localized. A ruptured pipe, failed valve, or cracked tank could release massive chlorine clouds that spread rapidly with the wind, overwhelming workers and nearby populations before evacuation was possible. Early plants lacked meaningful safeguards. Detection systems were primitive or non-existent, and many leaks were only discovered when workers collapsed. Protective equipment was minimal, often limited to cloth masks that provided no real protection. Emergency shutdown procedures were manual and slow, requiring workers to approach leaking systems directly, frequently at the cost of their lives. The danger was magnified by urban placement. Many chlorine plants were built near cities, rail hubs, or ports to facilitate distribution. When accidents occurred, toxic clouds drifted into residential areas, killing civilians far beyond plant boundaries. Entire neighborhoods were evacuated, and long-term health effects persisted among survivors. The parallels to chemical warfare were impossible to ignore. Chlorine had been used as a weapon during World War I, and industrial plants effectively stockpiled it in quantities rivaling military arsenals. Western governments and public health agencies began to recognize that civilian chlorine compression plants represented de facto chemical weapons sites without military security or containment. Environmental conditions added further risk. Heat increased pressure inside storage vessels, while corrosion weakened metal from within. Many catastrophic releases occurred during routine maintenance or equipment aging rather than dramatic accidents. In several cases, plants operated for years with known defects because shutting them down disrupted critical supply chains. By the mid to late 20th century, regulations tightened dramatically. Many countries banned large-scale chlorine compression facilities near populated areas, replaced chlorine with safer alternatives, or required conversion to on-site generation systems that eliminated bulk storage. Some nations effectively outlawed traditional chlorine compression plants entirely. The chlorine gas compression plant stands as a cautionary example of industrial ambition crossing into mass hazard. It did not need malicious intent to become a weapon. By concentrating a battlefield toxin into pressurized infrastructure, it created a machine capable of killing indiscriminately at national scale, earning its place among heavy systems deemed too dangerous to tolerate. Open mercury retort furnace vaporized poison in mining regions. The open mercury retort furnace was one of the most hazardous machines ever used in mineral processing, turning entire mining regions into long-term toxic zones. Designed to recover mercury or separate mercury metal amalgams, these furnaces operated by vaporizing mercury directly into the air, exposing workers and surrounding communities to a poison that attacked the nervous system silently and irreversibly. Open retort furnaces were widely used from the 18th through early 20th centuries in gold, silver, and mercury mining districts across Europe, the Americas, and Asia. The process was deceptively simple. Amalgam containing mercury was placed in heated vessels or open brick furnaces, where mercury vaporized at relatively low temperatures. The remaining precious metal was collected, while the mercury was theoretically condensed for reuse. In practice, much of it escaped directly into the environment. The primary danger was mercury vapor inhalation. Mercury vapor is colorless, odorless, and rapidly absorbed through the lungs into the bloodstream. Early retort furnaces had little to no sealing, and condensation systems were crude or absent entirely. Workers stood directly over heating chambers, breathing concentrated mercury fumes for hours at a time. Even brief exposure could cause tremors, confusion, and coordination loss. Prolonged exposure led to permanent neurological damage. The effects were cumulative and devastating. Miners and furnace operators developed severe tremors, memory loss, emotional instability, hallucinations, kidney failure, and progressive paralysis. The phrase "mad as a hatter" originated from similar mercury exposure, but in mining regions, entire workforces exhibited these symptoms simultaneously. Many victims were dismissed as mentally ill rather than poisoned, allowing operations to continue unchecked. Environmental contamination magnified the harm. Mercury vapors condensed on soil, buildings, clothing, and water sources around furnace sites. Rivers and agricultural land absorbed mercury, which then entered the food chain. Communities far from the original mining operation suffered neurological illness through contaminated fish, crops, and livestock. The poison persisted for decades, long after furnaces shut down. Fire and explosion risks compounded the danger. Mercury retort furnaces operated with open flames and volatile compounds. Structural failure or overheating could release large quantities of vapor suddenly, overwhelming entire crews. Emergency response was impossible because symptoms often struck within minutes, leaving victims disoriented and unable to escape. Despite growing medical evidence, economic pressure kept furnaces running. Mercury was essential to mining profitability, and safer closed systems were considered too expensive. In many regions, governments ignored the danger until population-wide health effects became undeniable. By the mid-20th century, open mercury retort furnaces were banned or phased out in many countries, replaced by sealed, regulated recovery systems. Cleanup, however, proved nearly impossible. Mercury contamination remains measurable in former mining districts today. The open mercury retort furnace stands as a stark example of the industrial poisoning at scale. It did not crush or explode. It slowly dismantled mines, communities, and ecosystems. By releasing vaporized poison into entire regions, it became a machine so destructive that nations were eventually forced to prohibit its use entirely. High-pressure riveted boiler system. Mobile explosives on wheels. The high-pressure riveted boiler system was one of the most dangerous technologies ever deployed in mobile industrial machinery, effectively turning vehicles, ships, and industrial equipment into moving bombs. Used extensively in steam locomotives, traction engines, ships, and early industrial plants, these boilers stored enormous amounts of energy under pressure, often with construction methods that could not reliably contain it. Riveted boilers became common in the 19th and early 20th centuries as demand for steam power increased. Large steel plates were shaped and joined using thousands of rivets, creating pressure vessels designed to hold superheated water and steam. As operating pressures rose to improve efficiency, boilers routinely worked near the absolute limits of contemporary metallurgy. Minor flaws in materials or workmanship could have catastrophic consequences. The primary danger was structural failure. Riveted seams were inherently weaker than the surrounding steel plate and relied on uniform stress distribution to remain intact. Corrosion, metal fatigue, uneven heating, or poor riveting could cause seams to fail suddenly. When a riveted boiler ruptured, the release of stored energy was explosive, equivalent to detonating large quantities of high explosives. Entire boiler shells were torn apart, launching heavy metal fragments hundreds of meters. Mobility amplified the threat. Boilers mounted on locomotives, traction engines, or ships carried this explosive potential directly through populated areas. Failures often occurred in stations, yards, city streets, or ports, killing not only operators but passengers and bystanders. Some explosions leveled nearby buildings, derailed trains, or sank vessels outright. Detection of impending failure was extremely difficult. Internal corrosion weakened plates invisibly, while scale buildup caused localized overheating that could rupture metal without warning. Pressure gauges were often inaccurate. and safety valves were unreliable or deliberately disabled to maintain performance. Human judgment played a critical role, and fatigue or distraction could prove fatal. Operating conditions worsened risk. Boilers experienced constant vibration, thermal cycling, and mechanical stress, especially on uneven tracks or rough roads. Emergency maneuvers placed sudden strain on already stressed systems. Maintenance was frequently postponed to avoid downtime, allowing defects to grow unnoticed. Crew exposure was severe. Engineers and firemen worked directly beside the boiler, feeding fuel and monitoring water levels under intense heat. Many suffered burns, scalding injuries, or hearing loss even without catastrophic failure. Survivors of partial ruptures often carried lifelong injuries. Public alarm eventually forced change. Boiler explosions were widely reported and deeply feared, leading to early safety legislation, inspection regimes, and design reforms. However, even improved riveted boilers could never fully eliminate risk. The eventual shift to welded boilers, diesel engines, and electric power rendered riveted systems obsolete. They were not banned for inefficiency, but because their fundamental design could not provide acceptable safety margins. The high-pressure riveted boiler system stands as a reminder that mobility and stored energy are a lethal combination when materials and inspection lag behind ambition. These machines moved industry forward, but did so by carrying explosive force wherever they traveled, earning their reputation as mobile explosives on wheels. Unshielded X-ray industrial scanner. Radiation exposure without limits. The Unshielded X-ray industrial scanner was one of the most dangerous inspection machines ever placed into routine use, exposing workers and surrounding populations to invisible radiation without meaningful limits or protection. Designed to examine welds, castings, and structural components without destroying them, these early scanners brought medical-grade radiation into factories and construction sites long before its risks were fully understood or regulated. Industrial X-ray scanners began appearing in the early to mid-20th century as heavy industries sought non-destructive testing methods. Using powerful X-ray tubes, these machines projected radiation through metal objects onto photographic plates or fluorescent screens, revealing internal flaws. The technology was revolutionary, allowing engineers to detect cracks and voids that could cause catastrophic failures. However, safety lagged far behind capability. The primary danger was uncontrolled radiation exposure. Early scanners were often completely unshielded or only partially enclosed. Operators stood near active X-ray sources, sometimes holding components by hand while scans were performed. Radiation beams scattered unpredictably, passing through walls, floors, and nearby equipment. Unlike mechanical hazards, exposure was silent and painless, providing no immediate warning. Workers received cumulative doses far exceeding modern safety limits. Acute exposure caused burns, hair loss, nausea, and radiation sickness. Long-term exposure led to cancers, genetic damage, cataracts, and bone marrow failure. Many operators did not associate their symptoms with radiation until years later, by which time damage was irreversible. The danger extended beyond operators. Because scanners were used in open workshops, shipyards, pipelines, and construction sites, bystanders were often irradiated unknowingly. Entire crews working nearby received doses simply by being present. In some cases, radiation passed into adjacent offices or public spaces, exposing people with no connection to industrial work. Lack of regulation compounded the problem. Early industrial radiography was often performed by minimally trained personnel using improvised procedures. Warning signs, exclusion zones, and dose monitoring were rare. Some operators believed that X-rays were harmless outside medical settings, a misconception reinforced by manufacturers eager to promote rapid adoption. Accidents were frequent and severe. Misaligned equipment, stuck switches, or forgotten power downs resulted in prolonged exposure. Several documented cases involved workers unknowingly carrying active radioactive sources in toolboxes or vehicles, irradiating themselves and others over extended periods. As medical evidence mounted, governments began imposing strict controls. Shielding requirements, Licensing, training standards, and exposure limits were introduced. Many countries banned unshielded industrial X-ray scanners outright, mandating enclosed cabinets or remote operation. Portable, open-beam systems were restricted to specialized, highly regulated use. The Unshielded X-ray industrial scanner stands as a stark example of technological optimism overpowering caution. It delivered critical inspection capability, but did so by treating radiation as just another industrial tool. By exposing humans to invisible danger without limits, it became a machine whose continued use was deemed unacceptable, forcing entire nations to regulate or eliminate it entirely. Mechanical pile driver, urban use, ground shock that collapsed cities. The mechanical pile driver was a foundational machine of modern construction, enabling buildings, bridges, and ports to be anchored into unstable ground. In dense urban environments, however, early mechanical pile drivers proved so destructive that their use was restricted or outright banned in several cities and countries. The problem was not the piles themselves, but the uncontrolled shock waves driven deep into the ground with every hammer blow. Mechanical pile drivers became widespread in the late 19th and early 20th centuries as cities expanded vertically. These machines used massive drop hammers or steam-powered rams to repeatedly strike piles, forcing them into soil or bedrock. Each impact delivered enormous kinetic energy, transmitted not only downward but outward through surrounding ground layers. In urban areas, this energy propagation became catastrophic. Older buildings were often founded on shallow footings, brick foundations, or timber piles resting in soft soil. Repeated pile driving caused ground vibrations strong enough to crack walls, shatter windows, displace foundations, and collapse weakened structures. Entire rows of buildings developed structural damage simply from construction occurring nearby. The danger extended underground. Shock waves disrupted sewer lines, water mains, gas pipes, and early electrical conduits. Broken gas lines led to fires and explosions, while ruptured sewers caused subsidence and sinkholes. Because underground infrastructure was poorly mapped, pile driving frequently damaged systems operators did not even know existed. Human safety was directly affected. Buildings weakened by vibration sometimes failed without warning, trapping or killing occupants. Construction workers were also at risk, as unstable ground shifted beneath machinery and collapsing nearby structures sent debris onto work sites. In several documented cases, pile driving caused partial building collapses hours or days later, long after crews had left. Noise and psychological impact were extreme. Mechanical pile drivers produced relentless, thunderous impacts that echoed through neighborhoods for weeks. Residents reported cracked plaster, falling ceilings, and chronic stress. Public backlash was intense, particularly in historic districts where heritage buildings suffered irreversible damage. Municipal authorities began responding with regulation. Cities such as London, Paris, and parts of Germany imposed strict limits on mechanical pile driving in populated areas. Some banned drop hammer pile drivers entirely, requiring alternative methods. These included vibratory piling, hydraulic presses, or board piles, which applied force more gradually and with reduced ground shock. Insurance companies also played a role. Claims for structural damage became so common that pile driving projects were deemed uninsurable without mitigation measures. This economic pressure accelerated bans and restrictions. Modern pile driving has evolved significantly, incorporating vibration control, monitoring systems, and low-impact techniques. However, early mechanical pile drivers demonstrated a hard lesson. Force acceptable in open ground becomes destructive in cities. The mechanical pile driver was not banned because it failed to work, but because it worked too violently. By transmitting industrial force directly into urban foundations, it proved capable of collapsing cities from below, earning its place among heavy machines deemed too dangerous for unrestricted use in populated environments. Diesel exhaust underground loader, Unfiltered, enclosed space asphyxiation machine. The unfiltered diesel exhaust underground loader was one of the most lethal machines ever introduced into mining and tunneling operations. not because of mechanical failure, but because of the invisible atmosphere it created. Designed to move ore, rock, and debris efficiently in confined spaces, these machines filled underground environments with toxic exhaust, turning productivity gains into a direct threat to human life. Diesel-powered loaders began replacing electric and rail-based haulage in underground mines during the mid-20th century. They offered flexibility, mobility, and high power in areas where fixed infrastructure was expensive or impractical. Early models, however, were deployed without exhaust filtration, catalytic converters, or adequate ventilation standards. In enclosed tunnels, this decision proved disastrous. The primary danger was diesel exhaust itself. Unfiltered diesel engines produce high concentrations of carbon monoxide, nitrogen oxides, sulfur compounds, and fine particulate matter. In open air, these gases disperse. Underground, they accumulate rapidly. Carbon monoxide is especially dangerous because it is colorless, odorless, and binds to hemoglobin far more effectively than oxygen, leading to suffocation without warning. Operators often worked directly on or near the loader for hours at a time. Early cabs were open or poorly sealed, exposing drivers to concentrated exhaust plumes. Symptoms such as dizziness, confusion, headaches, and nausea were common and frequently ignored as fatigue. In many documented cases, workers lost consciousness while operating equipment, resulting in fatal accidents or being crushed by moving machinery. Ventilation systems were often inadequate for the increased engine power. Mines designed for electric equipment lacked airflow capacity to dilute diesel emissions, as multiple loaders operated simultaneously. Exhaust levels rose to lethal concentrations across entire sections of a mine. Rescue was difficult, as responders entering the same atmosphere were exposed to identical risks. Long-term exposure compounded immediate danger. Diesel particulates are carcinogenic and caused chronic respiratory disease, cardiovascular damage, and elevated lung cancer rates among underground workers. Unlike sudden industrial accidents, these illnesses developed over years, masking the scale of harm until epidemiological evidence became overwhelming. The risk extended beyond operators. Maintenance crews, surveyors, and electricians working intermittently underground were exposed without warning. Exhaust also migrated into shafts, refuge chambers, and access tunnels assumed to be safe. In several incidents, entire crews were overcome simultaneously, resulting in multiple fatalities. As evidence mounted, governments began to intervene. Many countries banned unfiltered diesel equipment from underground use, mandating exhaust treatment systems, sealed cabs, and strict ventilation standards. Some mines were forced to revert temporarily to electric equipment until compliant machinery was available. Modern underground loaders now incorporate particulate filters, catalytic converters, real-time gas monitoring, and automated shutdowns. These changes were driven not by efficiency, but by necessity. The unfiltered diesel exhaust underground loader stands as a stark example of a machine that functioned perfectly while killing silently. By introducing combustion engines into confined spaces without safeguards, it transformed underground work into an asphyxiation hazard, earning its place among heavy machines so dangerous that entire nations were forced to ban or radically restrict their use. Hydraulic fracturing sand blender. Early design, silicosis at industrial speed. The early hydraulic fracturing sand blender was one of the most dangerous machines ever introduced into modern energy extraction. Not because it exploded or collapsed, but because it delivered lung-destroying disease at unprecedented speed. Designed to mix and deliver vast quantities of silica sand for hydraulic fracturing, these machines exposed workers to lethal dust concentrations that silently damaged respiratory systems beyond recovery. Hydraulic fracturing expanded rapidly in the late 20th and early 21st centuries as energy companies sought to unlock oil and gas from deep shale formations. Sand blenders were central to the process. These large mobile machines received dry, crystalline silica sand, mixed it with fluids, and pumped the mixture at high pressure into wells to keep underground fractures open. Early designs prioritized throughput and reliability, not human exposure. The primary danger was respirable crystalline silica dust. Sand was transferred from trucks into open hoppers, conveyed by belts, dropped into mixing tubs, and agitated violently during operation. Each transfer released dense clouds of fine silica particles small enough to penetrate deep into the lungs. In open fields, operators often assumed dispersion was adequate. In reality, exposure levels frequently exceeded safe limits by dozens or even hundreds of times. Silicosis, an irreversible and often fatal lung disease, was the result. Unlike acute industrial injuries, silicosis develops rapidly under heavy exposure. Workers operating sand blenders began showing symptoms after only months or a few years rather than decades. These included shortness of breath, chronic coughing, chest pain, and extreme fatigue. As the disease progressed, lung tissue hardened and scarred, eventually leading to respiratory failure. Early sand blenders offered almost no protection. Enclosures were absent, dust suppression systems were minimal or non-existent, and operators worked directly on top of or beside active equipment. Respiratory protection was often inadequate, improperly fitted, or discouraged due to discomfort in extreme working conditions. Many workers were unaware they were being poisoned until damage was irreversible. Maintenance work was especially dangerous. Cleaning clogged conveyors, replacing belts, or inspecting hoppers required direct contact with accumulated dust. Vibrations and wind redistributed settled silica continuously, exposing workers even when blending was paused. The scale of exposure alarmed health authorities. Medical investigations revealed clusters of aggressive silicosis cases among relatively young workers with short industry tenures. Unlike traditional mining silicosis, which developed slowly, fracturing-related cases progressed at alarming speed. Regulatory response followed. Several countries and regions banned open sand handling systems entirely, mandating enclosed blenders, vacuum transfer, wet handling, and real-time dust monitoring. Early blender designs were effectively outlawed or forced out of service due to unacceptable health risk. Modern fracturing equipment incorporates sealed systems, automation, and strict exposure controls, but only after widespread harm occurred. The early hydraulic fracturing sand blender stands as a modern example of how industrial speed can outpace occupational safety. It transformed a natural material into a biological weapon against its own operators, earning its place among heavy machines so dangerous that governments were forced to step in and stop their use. PCB coolant. Transformer system. Electrical power with permanent toxic legacy. The PCB coolant transformer system was once considered a triumph of electrical engineering, enabling reliable power distribution at scales never before possible. In time, it became one of the most widely banned industrial systems in the world, not because it failed electrically, but because it left behind a toxic legacy so persistent and dangerous that entire nations were forced to eliminate it. Polychlorinated biphenyls, known as PCBs, were introduced in the 1930s as dielectric coolants for transformers and capacitors. They were chemically stable, non-flammable, and exceptionally effective at dissipating heat. For electrical utilities, this made them ideal. Transformers filled with PCB coolant could operate in dense urban environments with reduced fire risk, powering cities, factories, and transportation networks. The danger lay in PCB chemistry itself. PCBs are highly toxic, bioaccumulative, and resistant to natural breakdown. Early transformer systems were not sealed to modern standards. Leaks occurred during normal operation, maintenance, and accidents. PCB oils dripped into soil, seeped into groundwater, and vaporized into indoor air. Workers handling transformers were routinely exposed through skin contact and inhalation. Health effects were severe and long-lasting. PCB exposure was linked to liver damage, immune system suppression, endocrine disruption, reproductive harm, and increased cancer risk. Neurological effects included memory loss and developmental impairment. Unlike many industrial toxins, PCBs accumulated in body fat and remained for years, compounding damage over time. Children exposed indirectly through contaminated food or environments suffered permanent developmental consequences. Environmental contamination expanded the impact far beyond work sites. PCBs released from transformers entered rivers, lakes, and marine ecosystems. Fish and wildlife accumulated high concentrations, making entire food chains toxic. Even communities with no direct industrial exposure were affected through contaminated water and food supplies. Cleanup proved extraordinarily difficult, as PCBs bind to sediments and resist degradation. Fire and explosion events worsened the threat. When PCB-filled transformers burned, they produced dioxins and furans, some of the most toxic compounds known. These byproducts contaminated large areas, forcing evacuations and long-term exclusion zones. Firefighters and emergency responders faced extreme exposure risks during such incidents. By the 1970s, scientific evidence had become overwhelming. Governments across North America, Europe, and parts of Asia banned the manufacture and use of PCBs in electrical equipment. Existing transformers were phased out, removed, or sealed under strict regulation. Disposal required specialized high-temperature incineration or long-term hazardous storage, adding enormous cost. Despite bans, the legacy persists. Aging infrastructure, contaminated sites, and buried equipment continue to pose risks decades later. Billions have been spent on remediation, yet complete removal remains impossible in many regions. The PCB coolant transformer system stands as a lesson in unintended consequence. It delivered electrical reliability while embedding permanent toxicity into the environment. By prioritizing performance and fire safety over chemical impact, it created a machine whose danger outlived its usefulness, earning its place among heavy systems deemed too hazardous for continued use by entire nations. Unregulated cyanide heap leach system. Open-air chemical disaster. The unregulated cyanide heap leach system was one of the most environmentally destructive mining technologies ever deployed, transforming vast landscapes into open-air chemical hazards. While it offered a cheap and efficient method for extracting gold from low-grade ore, its uncontrolled use led to widespread contamination, so severe that entire countries were forced to ban or tightly restrict the practice. Heap leaching became popular in the late 20th century as gold prices rose and easily accessible deposits were exhausted. The system involved piling crushed ore into massive heaps, often covering entire hillsides, then spraying the material with the cyanide solution. Cyanide bonded with gold particles, allowing the metal to be collected from drainage systems beneath the heap. In theory, the process was contained. In practice, early and unregulated systems were anything but. The primary danger was cyanide itself. Cyanide is acutely toxic, capable of killing humans and wildlife within minutes by preventing cells from using oxygen. In unregulated heap leach operations, cyanide was handled in enormous quantities in open environments. Liners beneath heaps were often absent, poorly installed, or easily punctured by sharp rock. As a result, cyanide solutions leaked directly into soil and groundwater. Rainfall and flooding magnified the risk. Heavy rain caused leach heaps to overflow, releasing cyanide-laced runoff into rivers and streams. These releases killed fish instantly, poisoned livestock, and contaminated drinking water for downstream communities. In several documented incidents, entire river systems were rendered biologically dead for hundreds of kilometers. Airborne contamination added another layer of danger. Cyanide solutions evaporated hydrogen cyanide gas under certain conditions, particularly in warm climates. Workers and nearby residents were exposed to toxic fumes without warning. Symptoms included headaches, dizziness, respiratory distress, and sudden collapse. Protective equipment and monitoring were often non-existent. The scale of damage extended beyond human health. Cyanide spills destroyed ecosystems that took decades to recover, if they recovered at all. Birds, insects, and mammals died en masse after contacting contaminated water. Agricultural land became unusable, and local economies collapsed as fishing and farming were wiped out. For years, mining companies argued that heap leaching was safe if managed correctly. However, repeated disasters proved otherwise. By the early 2000s, public opposition and scientific evidence forced government action. Several countries and regions banned cyanide heap leaching outright, citing unacceptable environmental and public health risks. Others imposed strict regulations that effectively eliminated unregulated systems. Cleanup proved extraordinarily difficult. Cyanide breaks down relatively quickly, but heavy metals mobilized by the process remained in soil and water long after operations ceased. Tailings heaps continued to leach contaminants for years, requiring constant monitoring and costly remediation. The unregulated cyanide heap leach system stands as a textbook example of industrial efficiency overwhelming environmental responsibility. It delivered gold at low cost by externalizing risk onto communities and ecosystems, by turning entire landscapes into chemical processing sites without safeguards. It became a machine so dangerous that nations were compelled to ban it entirely, leaving behind scars that still define mining disasters today.